Welcome from the U.S. Fish and Wildlife Services National Conservation Training Center in Shepherdstown, West Virginia. My name is Katie Poston, and I would like to welcome you to our webinar series held in partnership with the U.S. Geological Survey's National Climate Adaptation Science Center. Today's webinar is titled A Coastal Hazard Assessment with High-Resolution Data, a Pacific Island Case Study. And we are happy to have Dean Gesh with us today. And we have Heather Kirkering, who is the Pacific Islands Climate Adaptation Science Center Science Coordinator, here to introduce our presenter today. So thanks, Heather.
Yeah, aloha, everybody. Dean Gesh has been one of our PIs for this project, so we're very excited. He was willing to provide this presentation to you. He is a research physical scientist with USGS. And since 1992, he has conducted topographic science research at the Earth Resources Observation and Science Center at AROS in Sioux Falls, South Dakota, where he is the principal investigator leading the Coastal Changes and Impacts Focus Area and the Integrated Science and Applications Branch. His research topics are sea level rise vulnerability assessments, topographic change analysis and monitoring, hurricane storm surge mapping, elevation data accuracy assessment, and topographic data development. And his academic background includes a bachelor's degree in physical geography from Carroll College and a master's in geoscience from Murray State University and a PhD in geospatial science and engineering from South Dakota State University. So sounds like you're pretty qualified to keep talking. Thanks, Dean.
Heather, thanks for the great introduction. Also the invite to participate in this webinar series. I'm honored to present this work. It's the work of a lot of people as these kind of presentations go, so hopefully I can do it justice. And as we've heard, it's sponsored in large part by the PICAST, or the Pacific Islands Climate Adaptation Science Center. So we're grateful to that, and we'll dive right in and hopefully share some results that are relevant. So this is a headline from just last Friday, last week Friday, day after Thanksgiving. So this is the area that we're going to look at as the focus of the case study today. So talking about inundation and all the things associated with that. So just last week there was an event where there was very high waves. They were peaking at nearly 16 feet. That's a quote right from the article there. And you can see some pictures. So direct impacts and some real relevance to the work we're trying to do here and the results that we're having. Realizing that probably not everyone's familiar, even maybe a little bit, with Republic of the Marshall Islands, or what I'll call RMI. Just got some intro stuff there. So this is an aerial shot of the atoll. It's located in the Central Pacific, southwest of Hawaii. So the Marshall Islands, or RMI, are about halfway between Hawaii and Australia, as a little inset map shows there. So pretty remote in a lot of ways from other locations that we're used to, but right there in the Central Pacific. Just some aerial shots of parts of the atoll. This one is looking eastward along the southern part of the atoll. And in this case, the open ocean is on the right, and the lagoon, or the atoll lagoon, is on the left there. So you can see the road, and in the distance, the international airport. The reef flats, coral reef flats, all the things associated with typical atoll landforms. Another one here, further down the atoll. Again, the ocean on the right and the lagoon on the left. This is the urbanized area at the east end of the atoll. It contains Majuro, the city of Majuro, which is the capital of RMI. So quite built up, quite densely populated, residential, commercial, industrial areas, that sort of thing. And then another one with the lagoon in the foreground in this case, and the open ocean beyond the land in the background. So hopefully these shots give you an impression of the low-lying nature of the atoll and thus its vulnerability. So it's an island location, and you can see that it's completely surrounded by water and very thin strip of land, as atolls generally are. So we'll have more of these as we move on. And then just a shot along the shoreline of one of the islets that's in the northern portion of the atoll. So tropical location, obviously some beautiful scenery. So just look at that type of thing. And then from a couple months ago, this is interesting. Heather, thanks for pointing this out. think I got this from you, a declaration of a national climate crisis in RMI. So this is something that the national legislature in RMI did, and it's recognition by that national government of the severity of climate change issues and impacts for the country. Statement here by the president, again, reemphasizing the severity of the direct climate issues and climate change impacts that the government is facing. So just kind of emphasizes the critical needs in this area. Okay, that's a brief intro to Majuro. That's our case study, but I want to back up and give a little bit broader context for where some of this work falls. The general topic of integrated coastal elevation models. It's part of a project that we call CONED, the Coastal National Elevation Database. And a primary product there are these high-resolution topographic bathymetric digital elevation models with high spatial resolution, high vertical accuracy. So these are merged coastal elevation models. So they have the water depth information, near shore water depth or the bathymetry, and then the land information, and then it's a seamless topographic surface across that land-water interface. When I say high spatial resolution, these are 1 meter spatial resolution models and centimeter level vertical accuracy, so very high vertical accuracy. And then we'll look at how these models are used for coastal inundation exposure assessment, the Majuro Atoll case study, and then at the end just a couple brief examples of some other areas where CONED is doing work and the type of things we're looking at there. So a little bit more about CONED. I want to acknowledge Jeff Danielson, my colleague, who's the CONED projects chief here at AROS. But as I mentioned already, that the two main components of it are development of these high-resolution integrated elevation models, what we call CONED TBDEMs, and then the associated research with that. So that's remote sensing research related to different sources of 3D or elevation information and how that can enhance and produce produce improved elevation models. Just some quick screenshots there of some of these areas where we produce these high-resolution integrated models. And then under stakeholders, a whole list there of folks that are involved. I want to acknowledge what we call the short name, the USGS Coastal Program. The long name is the Coastal and Marine Hazards and Resources Program. So that's a major sponsor of the CONED activities. And then a lot of the other users, if you will, of CONED information. A couple different storm surge models, the National Water Model, which is getting a lot of attention, at least within USGS and within NOAA. For instance, they use the CONED models to provide key bathymetry in estuaries, and that's useful for coupling together inland hydrologic flow models and coastal water level models, so an important use there. And then there's a number of sea level rise and coastal resiliency tools and viewers that also make use of the CONED information. So that's just really a short list of some of those things where CONED factors in. Just a map of the current coverage of CONED models, and then some ongoing work, and then where CONED is planned to work. So this is for CONUS and Hawaii. Obviously it doesn't include Majuro, but that's included as well. So the red area along the northeast Atlantic coast there, that's the Hurricane Sandy impact region. So that was a big driver for a lot of CONED development, a lot of CONED work. And then kind of likewise in Florida, where you see where we're going to have work starting up fairly soon. These integrated models are going to be produced for that area that was subject to the impacts of Hurricane Florence. So we're driven by a lot of these ongoing events and coastal hazards. Some examples, more examples. This is a recently completed CONED TBDEM in the Pacific Northwest. And that's a validated high-res model, and that's a critical component for what's called Cosmos. Some of you may have heard of that, the Coastal Storm Modeling System. That's a big USGS activity where sea level rise and effects of storms are modeled along the West Coast. So CONED provides the key elevation input for that system. And then some current work that's really ramping up right now is a major upgrade of the northern Gulf of Mexico model, or what we call NGOM. We produced a model there at a bit lower resolution a number of years ago. That's going to be a complete upgrade, so that's being upgraded to a 1 meter model. There's a whole bunch of new lidar data and bathymetry data for that area, so those are being integrated. This is really a key data set, and a key partner for this work is the Louisiana State Agency. It's called CPRA, stands for the Coastal Protection and Restoration Authority, and that's the state agency that guides all the coastal resiliency work, coastal restoration and protection work. And they put out a master plan every 5 years, and this CONED model is used as a key component of developing that master plan and the strategies for coastal restoration. So that's some important work that's taken a lot of time already and will be of our CONED staff. Okay. So there's a brief introduction to CONED. Now back to our case study, so where we're going to illustrate the development and application of a high-res, high-accuracy integrated coastal elevation model, in this case for Majuro Atoll in RMI. So just some quick shots at the beginning of the 1 meter digital elevation model, or the DEM, that was produced for this area. I'll have a little bit more detail about how that was produced, and then a lot more detail about how that was used. So we produced this model for the connected, what I'll call the connected portion, and by that I mean a continuous road from kind of the southern half of the atoll. So that runs a length of about 48 kilometers, or about 30 miles. So we've got this 1 meter model that covers that area, and the aerial shots that I showed you earlier all come from that study area there. So we're just going to move around the atoll kind of from the northeast over to the west. You can see some detail with this model. Kind of that red feature that's in the upper right, that's the highest point on the island, an elevation of about 16 meters. And but that's an anthropogenic landform, so that's the trash landfill. So again, gives you an idea of the low relief nature of this setting. That the highest feature is actually a man-made feature there. We move around to the west, just again showing the thin width of the island in some places. And now we're in the rural area to the west. And again, that red area, that's kind of in the central portion there. That's the highest natural feature on the island. And that's those are some kind of low hills, I guess high hills for this area, but what we would call lower hills of about 6 meters in height. So that's the highest natural feature on the island. Again, a little bit more about the geography of where this falls. There's roughly 2 parallel island chains in the Marshall Islands. So Majuro Atoll is in the eastern part. It's called the Raytac chain, which stands for sunrise. And then just some basic stats and facts about RMI. So, you know, quite a number of islands, but those are spread out over a fairly large area. When you total up the whole land area, though, it's pretty small. It's about 70 square miles. Again, overall, the average height is very low, obviously right next to the ocean. And a large portion of the population, the total population for the country, resides on Majuro. And most of that population resides on the eastern portion of the east end of the atoll, so very dense population there. Another atoll in RMI is, you may have heard of as Kwajalein. There's a large U.S. military presence there. And kind of an interesting sidelight for this one, perhaps you've read the book or seen the movie Unbroken, an account of a prisoner of war, a pilot, U.S. pilot, and he was an Allied prisoner of war held on this island, and that was known by the prisoners there as Execution Island. So it was controlled by the Japanese during the early part of the war until the Allies were able to take over those lands. So some interesting history in the different portions of the Marshall Islands. Part of that interesting history you've probably at least heard of is the nuclear bomb testing that took place after World War II. So that took place primarily on Bikini Atoll and Inuitak Atoll up in the northwest there. That's a huge part of the Marshall Islands history, and it resonates even to this day. So, here's a picture of a building on Majuro, and if you can see there on the sign, it says the Bikini Atoll Town Hall. So we're some 500 miles away from Bikini, but that was obviously evacuated as a result of that nuclear testing, and a lot of those Bikini Islanders were relocated to Majuro, and still, but yet they still function as a group, with their own government, and that's why we have things like the Bikini Atoll Town Hall here on Majuro. So again, a direct result of that nuclear testing history. One of the smaller islands on the north part of the atoll, Egypt, is home to where many of these Bikini Islander families settled. RMI is an independent country, but it's closely aligned with the U.S. under what's called a Compact of Free Association. That allows the U.S. to have a military presence there. The U.S. provides military protection for the country. Other things, the U.S. dollar is used. Marshall Islanders are not U.S. citizens, but they can freely come and go from the United States. So there's, again, a close alignment of the countries. That compact is up for renewal in a few years. As you can imagine, there's a large economic impact of that. There's a large amount of aid that the U.S. Provides to the Marshall Islands. So that's a big part of the kind of geopolitical landscape of the Marshall Islands. Another part of that is the growing Chinese influence in the Pacific, and RMI is not immune to that. So this is just a smattering of recent articles in the press that kind of talk about details of that. I'll just flip through these really close. So it's it's got some complex components in the geopolitical landscape, and these are kind of overlaid, if you will, with the physical threats, the climate change threats that we're going to talk about today and more. So just thought that might be useful as background information for those of you that aren't really familiar with that setting. Okay, back to the physical setting, just a simple diagram. Hopefully this is a review from your, physical geography or geology 101 classes, kind of how atolls are formed. It's an evolutionary landform from volcanic islands in the ocean, and then as erosion and subsidence takes place, these fringing reefs become barrier reefs, and then eventually those reefs, those limestone reefs, are the only thing that are left, and the rest of the volcanic landform is submerged there. So that's the case with Majuro and these other atolls in RMI and in the Pacific. Just kind of a cross-section of that, and I'll refer back to this later, but you get this steep drop-off, which again is the result of that initial volcanic landform. But the resulting, the current atoll, the current exposed landform is this carbonate-based atoll landform. Okay, sea level rise, obviously a big a factor in the Pacific, not just in the Pacific, but everywhere, but since we're talking about that as a case study today. So just a simple diagram of the components that add to that. I'm sure you've seen many like this. This comes from the IPCC. Thermal expansion, it's not labeled on there explicitly, but thermal expansion of the ocean is a big factor for sea level rise, as well as the inputs that you see from the ice sheets and all those sort of things. Well, the ocean absorbed that, the heat from the ever-warming Earth system. So that's an important factor, and certainly is the case with what we're seeing in the Pacific. As we look at the kind of the historical sea level rise trend in Majuro, there is a tide gauge at the east end of the atoll on the lagoon, and it's been operating for 30 to 40 years, that sort of thing. So what we see there is an average of, in this case from this NOAA gauge, 3.6 millimeters per year. That's actually pretty close to the global mean sea level rise average that we're seeing. So that trend is at least following there. But as we'll see, there's a lot of projected acceleration to that, and that's going to continue to be an issue, not just in RMI, but any of these small island states. IPCC, there's a lot of information in their most recent assessment report about this, how the The Central Pacific is a hotspot, if you will, projected to be a hotspot of sea level rise, meaning that the global average, or the sea level rise, the sea level change that's going to happen in that area is going to be generally more than the overall global sea level rise. It's kind of a well-documented projection from a lot of studies, and there's plenty of maps in there that show that. So just a couple here. So you can see that hot spot in the Central Pacific. On this map, it's over to the right again, higher than the global average, and likewise on this map. So well documented. Whatever emission scenario you're looking at, or what IPCC calls the RCPs, there's still an acceleration in the latter half of the century in any of those. Obviously, the magnitude of that changes depending on which emission scenario you're looking at, but that's a factor that's always going to be there. The remote sensing record of the sea level change since the early 90s shows this global average sea level rise of about 3 millimeters a year. So that's, again, over the whole globe, but that does vary quite a bit regionally. So this is a graph of that shows that historical record based on remote sensing, global remote sensing. And again, so we look at the paleo record, the instrument record since the early 90s, and then the modeled projections all fall into the same thing. So there's going to be a significant, projected significant acceleration in sea level rise, and that's obviously going to affect these oceanic locations like RMI. Okay, specifically to what we're doing there and the techniques that we've applied in this inundation exposure assessment for Majuro. One of the big things we look at is uncertainty in sea level rise assessments. And that can certainly come in these the projections of the contributions of things like the polar ice sheets, Greenland and Antarctica, and that needs to be factored in. What we're concentrating on is the uncertainty in the input data sets. Obviously, when you measure water level change, that's got to be in reference to a datum. So there's uncertainties in those water level datums and how things are measured. And then specifically also with the elevation data, the input geospatial data. So those are the things, these last two is where we can really get an idea of how that uncertainty is going to affect our inundation exposure modeling. And that's what this example will show. Been a good amount of research in the last 5 to 10 years about how uncertainty, specifically vertical uncertainty, factors in. Just a snapshot of some of those papers. Some really good results, but despite these results, there's still many sea level rise and coastal flooding assessments that do not account properly for that vertical uncertainty. They just choose to ignore it, and that's obviously something we think is not the way to do it, and this example hopefully will show you that as well, why that's really important to look at the quality of the elevation data and how to handle that uncertainty in a rigorous and quantitative manner. So again, that vertical uncertainty, it affects a couple of things when we look at a sea level rise or coastal flooding assessment, the selection of the parameters. So what's the increment of sea level rise that you can, or water level increase that you can effectively model with high confidence? And then how far can you project that out? Those are directly tied to the vertical uncertainty of the input data. And then how you map that spatially. You know, every assessment wants to have a map, spatial maps of how that projected inundation is going to look. So again, both of those are affected by the vertical uncertainty. So I'm not going to spend a lot of time on this, a lot of detail, but there's some simple ways to calculate a couple parameters, what I've called here minimum sea level rise increment, or again, that could be generalized more to minimum water level increment. And you know, those are based on a contour line approach, because raising the water level on a DEM, that's really easy to do, especially in a digital GIS environment. You can take a DEM, you can raise the water level on it and call that an assessment. Very easy to do, but in a lot of ways very dangerous to do if you don't account for the quality of the data. So we want to make sure we're doing that in a way that reflects the quality of the data. So, you know, raising that water level, it's inherently a contouring operation. So that's why we apply these contour line standards, and we can do that at different confidence levels. Again, a little bit of technical detail here, but the way we measure the accuracy of an elevation model, root mean square error, that's the industry standard way of doing that. That's got a confidence level associated with it. That confidence level can be transformed in simple ways. So again, this minimum increment, if you want to model it at a specific level of confidence, that's directly tied to that measure of vertical uncertainty, or the RMSE. Now, you can turn that equation around, and this is how it's most useful. If you want to measure a certain amount of sea level rise or coastal inundation, what is the quality, what is the accuracy of the elevation model that you need? So this simple relationship can help you determine that, and we'll show that. Now, 1 foot is commonly used, at least in the U.S., in local and regional assessments. 1 foot is commonly used as that increment. And if you're using, industry standard lidar elevation data, which is really the best source of high accuracy elevation data, collected in a remote sensing approach, the accuracies that you show here, that I'm showing, about 8 centimeters, 8 to 15 centimeters, industry standard lidar can attain those accuracies. So if you have lidar data, that's great. That's what you want to use. And then you're not modeling an increment that's too small given the noise or the error in the elevation data. But when you don't have elevation data of high accuracy like lidar derived, there's a lot of areas that don't. Global DEMs are often used, but their vertical accuracy is much worse. Now, not to badmouth these global DEMs, they're actually excellent for a lot of applications. But when you're looking at modeling small increments of water level increase, which is what you would do on a low relief area like Majuro or any low relief coastal area, they're severely limited for that, and they really should not be used for that. And we'll talk more about that in a little bit. So these are some of those sources there. There's been some improvements. SRTM, the Shuttle Radar Topography Mission, is one that's been widely used. There's been some recent improvements to that by NASA, some reprocessing of that helped a lot, but it still isn't at a level where you can model these small increments, and by that I mean sub-meter increments of water level increase. In the U.S., we have other sources, the USGS National Elevation Data Set, what we call the NED. Again, still and better, but still somewhat limited. But we're looking at, again, if we don't have LiDAR, we have to look at sources like UAVs, unmanned aerial vehicles, or what we prefer to call UAS, or unmanned aerial systems. That's commonly referred to as drones. And with that, we can produce elevation data that's LiDAR quality, really in the same ballpark, the same accuracy level as LiDAR data. And that is really valuable when we look at places like Majuro. And that's what we'll be looking at here. So, our UAS-derived DEM that we produced for Majuro, I have some more details about that in just a second, is really the only one for Majuro that allows us to model these small or sub-meter increments of inundation with high confidence. Again, you can get lost in the numbers on the slide a little bit, but you're looking, with these global elevation models, you're looking at water level increases of meters, which would cover the entire island. So they really are not of any use when you're trying to model inundation in an environment like this. Okay, a little bit more about the DEM, how it was made, and then how it was applied. This is an example of that aerial image, kind of the same image you saw before, but that's kind of a mosaic of those aerial images that were collected by the UAS or by the drones, and then those were processed into this high-resolution, high-accuracy DEM. Some 20,000 photos were collected, over a field campaign of about 10 or 12 days, I think it was. 5 centimeters, really high-resolution photos, and then at the same time, over 100,000 RTK GPS points were collected for validation, also for control. Some of those, a very small subset, were for control of the aerial photography, and then a large validation data set collected with GPS, RTK GPS there. So structure from motion might be a term you've heard, maybe you're familiar with, maybe not, what we call SFM. It's really just a fancy name for kind of good old-fashioned stereo photogrammetry that's been done for years, but with a twist and much improvement. So, stereo photogrammetry would derive elevations from overlapping aerial images, a pair, 2 images. Well, with structure from motion, many images, many overlapping images are collected and are used to derive elevation, and that allows a much better, much more accurate depiction of elevation. So the motion in this case is the motion of the platform or the motion of the drone. The drone flies, it moves, it collects these overlapping images, and that's where the term comes from, structure from motion. So the results of this structure from motion processing of the photos is a point cloud. So that's just like lidar, and that's really good. And then that high accuracy, high density point cloud is it's an X, Y, and a Z. Basically, each point has an elevation and obviously location, and then those are used to generate a raster DEM of the land surface, and that's what was done from Majuro. Now, I said it's a TBDEM, so it's topographic bathymetric. So the topo side is what was done with the structure from motion from the drone imagery. The bathymetry side was a number of sources, including satellite imagery, and we do what we call satellite-derived bathymetry, some sophisticated processing there. There was also some sonar data that was merged in, so it's a multi-source elevation model. Includes satellite imagery for the bathy and these other sources. And finally, there's the DEM itself. So that covers the land area, all the bathymetry of the lagoon, and then the deeper offshore bathymetry on the eastern half of the atoll. And again, that's that steep drop-off there. So if you remember back to that diagram that kind of showed the classic atoll landform, that steep drop-off, that's what we're seeing on the right. And then what we have what we call spatial metadata. So we have this for every CONAD TBDEM, so the user can trace back to the origin of every elevation in the elevation model back to its source data, and then all the metadata associated with each of those source data sets, the quality and how it was processed, all that sort of thing. So very useful spatially explicit metadata there. Lots more details are available. I really just glossed over it, but there's some USGS publications here. And then, of course, the data set itself, the 1 meter DEM, is available publicly and freely as a USGS data release. Okay, so we've touched upon this a little bit already, but now let's apply this to the Majuro site. So why does elevation accuracy matter? Well, this shows kind of the accuracy or the noise level of a couple different types of DEMs. If you're looking at a nominal 1 meter sea level rise or inundation level, you have to be not within the noise level of the DEM, and that's what we're gonna demonstrate here. So again, here's a couple of these DEMs, a couple of the global DEMs in the middle and on the right, and then our DEM from the aerial imagery. And we apply that, again, this is a view from the lagoon, very low relief area. You can see these huge error bars. It would really be worthless to try and model any level of inundation with those huge error bars. So we need a much better accuracy, and that's what we get with the DEM we produce there. So 7.5 inches is about 19 centimeters. That's our accuracy expressed as an RMSE. I'm having in inches here because the audience, if you will, the intended audience in the Marshall Islands uses those English units a lot. So that's why I'm kind of going back and forth. So we've expressed a lot of this in both metric units and in the English units here. So that's why you're seeing both. We can change that confidence level. So an RMSE, or our 7.5 inches there, our error, that's about a 68% confidence. That can be translated to 95%, and that gives us at the 15-inch level, about a little bit under 40 centimeters at 95% confidence. And that elevation can be plus or minus. So that's why we the true elevation would be within that plus or minus, so that's why we show both. So this is how we get the allowable increments, what I'll call the allowable increments of inundation to be modeled. It's tied directly to the accuracy of that DEM. So this is where we get 15 inches of inundation and then 30 inches of inundation. So where we can be sure that we're not using the increment that's within the noise level or within the accuracy of the DEM. And that's our minimum increment of sea level rise. And again, that's tied directly to the accuracy, and it's an expression of how well that contour line or how well that raised water level is placed vertically on the landscape or on the DEM. So these are the 3 increments we're using. They're measured above the high tide line because anything below the high tide or being high water is already subject to periodic inundation. So we can measure a 15-inch inundation with a 68% confidence, 30-inch at 95%, and a 45-inch at 99%. So the original thought was to look at 1-foot increments for mitigation planning in this work. We're close to that, but the DEM through testing doesn't quite support that. So that's why we're a little bit off a foot. You know, a lot of the details and how this is derived is published in a paper that I'd be glad to make available if you really want the details. The paper was published a year ago, and I've got some more info on that at the end. Okay, so that takes care of the proper parameter selection for our study. Now we have to actually map that inundation onto the landscape using the DEM. There's a couple different ways to do that. The simplest way that's been done most of the time is what's called deterministic. So again, you just raise the water level on it, and the map, the location and extent of where that inundation happens is simply it's determined simply by where the elevation falls on that landscape. But you have no idea of the quality of that delineation. So it's a very limited approach. Kind of a modified version of that is where we at least take what we know about the elevation error, and we basically add that and subtract it from the projected water level, and that gives us a range. So that's why it's called modified deterministic, still a deterministic approach, but at least you can give a range and label that with a quantified confidence level. So it's a little better. The best way to do it is a fully probabilistic approach, and that's what we've done. Again, I'm not going to get into the details, but that's where the error characteristics or the error statistics are modeled and then applied in a Monte Carlo simulation. So you take those error characteristics, you produce what are called equally probable realizations of the DEM, you do the inundation mapping on those, and then you accumulate that through many, many, many simulations, the Monte Carlo approach, and then you have a full probability distribution of what's going to be subject to a certain level of inundation and a probability attached to that. So let's look at some results. That's the best way to do it. Got 4 areas I'm going to zoom in on. A and B are built-up areas in the eastern end of the atoll, the densely populated areas. C shows some infrastructure in the kind of the south-central portion. So you see the part of the international airport, and then the public water supply reservoirs, and then the west end, that rural end. Interestingly, that water supply runoff from rain is rainwater collection supplies most of the domestic water supply for the folks on Majuro, and they actually collect the runoff right from the runway and the airport area and collect that in these reservoirs. So that's an important area. Okay, so we look at marine inundation, what's called marine inundation, and that's where it has a direct hydrologic connection to the ocean or the lagoon, and that's easy to model in a raster sense in a GIS. And then we also do low-lying areas. So those are areas below the target elevation or the modeled elevation, but they're not hydrologically connected to the ocean. So these are sometimes called groundwater inundation areas, but they can also be inundated due to runoff and waves and the like. So they're places that will collect water or water will pond up. So the results I'm showing here are from the best approach, the probabilistic approach. So again, at that 1.25 feet or 15-inch projected water level, again, we can say these are the areas with a 68% chance, or what in IPCC terminology, likely, and that's given what we know about the error of the elevation data. So you don't see many areas here, but the dark blue are the marine inundation, the light blue are those kind of disconnected, low-lying, more internal areas. Go to our next height, 2.5 feet, again at the same probability level, and we see more areas that are subject again. So this is the projected inundation given the vertical uncertainty in the DEM expressed with a specific probability or chance level. And then at our highest one, a 68% chance, again, likely. So one thing to look at here is how some of these low-lying areas, I'll flip back and forth here between the previous one. If you look at some of those light blue areas, when we move to a higher level, then those become marine inundation, which makes sense because then at those higher water levels, that hydrologic connection comes into play. The water is high enough to get over some areas that were previously causing that to be disconnected. So that's an important thing to consider. Also, one thing we also did was we determined the source of marine inundation. In other words, we looked at whether the inundation was coming from the lagoon side or the open ocean facing side of the atoll. And in greater than 3/4 of the cases, so in 75% of the cases, that we looked at different water levels and different mapping approaches, all those sort of things, the percent of marine inundation coming from the lagoon was greater than that coming from the ocean side. And that makes sense. It's kind of well documented in other studies that the lagoon shore is generally lower in elevation than the ocean side, and it's also much less armored. It has less seawalls and riprap and that sort of thing. So that's an important consideration, is where that inundation is coming from. And then there's some areas that have been identified as being inundated simultaneously from both sides. So those, you could argue, are the most vulnerable areas. I mean, those are really those areas where it's very thin strip of land, and also very low elevation areas, part of the atoll that we see there. Here's this similar map. This is again at the highest water level we modeled, 45 inches, and then but a 95% chance again. So we can change that probability category, and again, using IPCC terminology, these are labeled areas to be extremely likely inundated at that water level, given what we know about the elevation error in the model. So some tabulated results. Obviously, it's you can measure the area. And in this case, it was also presented as the percent of the total atoll land area, the study area. So the deterministic results, they will always fall within that range of the modified deterministic approach, and you can see some of them highlighted there. The probabilistic result, again, that percent of that land area, it usually falls toward the lower end of that range. So that's an interesting observation. And then the probabilistic it's always less than the deterministic. So that was the case with all the results. So not only does deterministic not have any expression of the confidence, but it also seems to be over-predicting the amount of area that would be inundated. So it's really an approach that has a lot of shortcomings and really shouldn't be used. Same case there, just with the higher confidence level. So using the uncertainty provides better estimates and selectable risk levels. So it's a continuous field, this inundation probability, the results from the probabilistic approach. So you can select. Now I showed it at 68% chance and 95%, but that could be selected at anything, 80, 85, whatever. So that's a real advantage to have that selectable risk level. So that the way we've applied this high accuracy DEM allows us to do that. Just a quick one here to demonstrate that event-based inundation, kind of like we showed at the very beginning with the high wave event from last week. There's a system, PACIOS, which is the Pacific Island Ocean Observing System. They generate wave run-up forecasts. So a case here where there's a high wave event from a few years ago. And what this allows us to do now with this high-res, high-accuracy model is to have a spatial representation of where that inundation might happen, again, with an attached probability to it. As with all these exercises, there's certainly limitations of this, and these are some ones that are apparent, and I just want to make sure we touch upon these. It's a really good DEM, but there still has some uncertainty, and especially in forested areas, the structure for motion approach, it takes, when the drone takes pictures, it takes them of the top of trees in dense forested areas, tops of buildings, so that information has to be filtered out or removed, and then just the ground level has to be interpolated. So there's obviously some error there, and we see that in the DEM. We've captured a lot of the seawalls and a lot of the flood protection barriers, but we know not all of them are completely accurate. Some of them that might even be below the resolution of the DEM. So there's some issues there. And then a big one is the kind of inundation modeling we did. It's been called passive flooding or hydrostatic, a couple different names. It's really the simplest approach, and it's a good start, but it doesn't account for wave run-up and coastal erosion and all these dynamic processes. There's a couple of papers highlighted there on the right, lower right corner, published in the last year or so that demonstrate very clearly that when you add in the dynamic processes, especially wave run-up and that sort of thing, that really increases the vulnerable areas and the severity of it. So that's something that that does need to be added in addition to this kind of initial hydrostatic approach there. So that's a big one to keep under consideration. Okay, just a few other examples here of the inundation, some ground shots. Again, it's not just sea level rise that's going to increase, but these high tide events, or what are called king tides, and those come much sooner than even the highest rates of sea level rise. So that's important to keep in mind. There's a record of a lot of these events that happen on Majuro and the rest of the Marshall Islands. Again, low relief area. This is a national telecommunications facility right along the lagoon shore. There is a seawall there in front of it, but again, highly vulnerable. The country itself is looking at some pretty drastic measures about how you can have an engineering solution to some of these. Actually raising portions of the island and different facilities. Some press coverage of that. The local mitigation approaches that are already being used. You got to do best you can, protect things, in the best way possible. And this is an example of that. This is one of the drone images, and I'll direct your attention kind of the north center part of that. This is, just a bunch of material, refuse material that's piled up along the shore there to provide a berm to provide some level of flood protection. So it's obviously a critical issue and will continue to be. So, these kind of data sets and approaches are going to be helpful for this kind of planning. A lot of studies on the general vulnerability of atoll landforms. There's not complete scientific consensus about, kind of the rates of that and how that happens. There's some competing studies about how these islands can be adaptive to that. So, there's some good science that's being done, but yet more work needs to be done. And in either case, the data sets that go into the modeling and the mitigation planning and that sort of thing can certainly be improved, and that's what we believe we've done here with the work that we've done in Majuro. Those data sets are all available, again, publicly as a USGS data release, the many different scenarios and mapping approaches. So those are all available as a USGS data set out there for public consumption. A lot of details are wrapped up in a paper. This paper is in revision now. It's likely to be accepted pretty soon here and published shortly, hopefully within the next month or two. So again, if you're interested in details, those are available. And then for further information, a lot of the background information about this consideration of vertical uncertainty that we applied in this case, I'd be glad to supply these, point you to them if you have interest in a lot more detail. And then for CONET itself, back to that the larger topic, good website, data access through that website, and then a couple of good journal papers from a few years ago about the details about how these TBDEMs are put together. So direct you to a lot of that for further information. And then finally, just one on the ongoing efforts. This is a current project also sponsored by PICASC, and this is some work that's being done at a National Park Service site. I won't even try to pronounce the full name. I'll use the National Park Service abbreviation of PUHO. We're doing a similar type of inundation assessment here, but with some additions that cover maybe some of the shortcomings, if you will, of the Majuro work. So we have highly detailed data, 3D data from a couple of different sources, terrestrial lidar to get at these very accurate measurements of elevations of structures that will affect the flow. This is a highly significant cultural site on the west coast of Hawaii. So we've got lidar collected from UAS, we've got imagery for structure for motion, and then terrestrial lidar, working with our friends in Phil Thompson's group at UH. And the result of this will be that type of inundation assessment modeling. And the important addition here as well is there's wave sensors out in the ocean, so we'll have a good knowledge of the wave climate and the water level record of, if you will, seasonal changes and that sort of thing to apply to the inundation analysis projection and planning for this national park site. So that's some good work going on that's related and directly driven off of our previous work. So some takeaways hopefully you've gotten, but I'll just list these quickly. These high-res accuracy, high-resolution, high-accuracy models are really critical for doing these type of detailed coastal assessments. The global elevation models, not so much. They really shouldn't be used for that. Also critical is accounting for that vertical uncertainty, and we believe we've struck upon ways where that can be done in a rigorous manner and a very precise manner. So we've demonstrated that. And then this approach of using UAS, it works well in these remote locations where, kind of the traditional, standard approaches where you fly airborne on an airplane, airborne lidar, those can have really significant challenges logistically and cost-wise. So, UAS is a technology that has worked, and it can be adopted really and used by the local stakeholders and local entities. So that's an important development as well. Of course, thanks to many, many people. I just had the privilege of presenting this today. This is particular to the Majuro effort. Many names there. I'm sure I've left off a few, but a huge number of participants and supporters and collaborators, and certainly couldn't have done this work without all of those. So I certainly want to mention that here. And then with that, I'll close off and be glad to take any questions or comments. Thank you very much.
Katie says, thank you for the summary at the beginning of the status of coastal studies and publications in the U.S. states within the Pacific beyond Hawaii. Does USGS anticipate moving beyond Majuro to other atoll or coastal analyses in Palau or the FSM?
Yes, good question. We actually have done some work in FSM, the island of Ponape. It's a little bit different flavor from this. It's really there. It's about the resiliency of the mangrove forest, the fringing mangrove forest in Ponape. One of the big needs there is for a high accuracy elevation model. We don't have that in Ponape, so we've done some field collection of some very site-specific elevation data. But the goal there is to have eventually that type of high accuracy, high resolution data in Ponape. As far as other atoll locations within the Pacific, as you can imagine, there's been a good amount of interest in these results, and we've had discussions about other areas, specifically in RMI. None of those have come to fruition yet, but we continue to have those, and there's a lot of interest in that. Our sponsors at PICASC and other folks within USGS, specifically Dr. Dave Helweg, who's a liaison to the insular areas, these insular areas affiliated with the U.S., continues to seek opportunities for that and to seek efforts to do that. So we hope to do more of that.
And Heather says, are you able to talk about user of the data, specifically the Majuro government?
Yes, good. I did want to mention that. Thanks for the prompt, Heather. Yeah, one thing we know is that we presented a lot of this work initially. It's an ongoing project for numbers. We presented this to the representatives from the Majuro government and some of their consultants about a year ago. And at that time, they were looking at funds that for seawall construction. So I know they were very interested in this information for that use. We know it's also being looked at to do an initial screening of these low-lying areas where water can collect, whether that's connected to the ocean or not, but under certain water level conditions or even precipitation events where those can be, those areas can be located. So the data are being used for an initial screening for that. So just a couple examples of how that, how the data are being used for those type of planning.
All right, Katie says, yep, FSM is very interested in coastal analysis of upland, yep, since taro patches along the coast are important. Coastal plain between mangroves and uplands. And Benedict says, thank you, sir, for sharing the presentation. I was wondering if you're planning to include Majuro Airport in your future UAV fieldwork.
Yeah, good question. Actually, the Majuro Airport, I know when I was showing the DEM, there was a missing piece there. And when we look at the DEM we have for the area, it actually does include the airport area. Now, it was not collected with UAV imagery, though. The difficulty of flying over that sort of area with incoming and outgoing flights, that sort of thing. But there were portions of time where we were able to map the airport property with RTK GPS. So we have very dense survey points over that area. So the DEM, the portion of the DEM that covers the airport was collected with GPS data. Again, that's going to be much more accurate, on at least on a point-by-point basis, than anything derived from the UAV imagery. But that's how that portion of the DEM was covered, with GPS, RTK GPS points.
Right. And Martin asks, the Marshall Islands Conservation Society is undertaking similar work on 5 outer atolls, specifically focused on flood risk assessment. Would you and your office be available to discuss or assist us?
By all means, yes. I'm at the end there. I had the logos up for just a short period of time, but the Marshall Islands Conservation Society was listed there. So, yeah, they were a partner already in this work, and yeah, we'd be more than interested in that. I'm guessing some of the folks we work with are already aware of that, but by all means. So, facilitate a contact and my contact information or any of our team, and we'll be glad to visit about that. Yes, thank you.
A big thank you to our presenter, Dean, today, and thank you, Heather, for the introduction. And thank you all for tuning in.
Thank you.
Thank you.